Welcome to this explainer. Today we are embarking on a pretty incredible journey. We're going to transform from being just curious observers of the world around us into fully equipped methodical scientists. We're breaking down the absolute foundation of scientific investigation, giving you the real tools you need to understand the physical universe in a structured, accurate, and honestly, fascinating way. Let's get into it.
Here is our roadmap for today. We'll be looking at science in daily life, stepping inside your science laboratory, going over physical quantities and units, mastering your measuring instruments, exploring density and the scientific process, and wrapping up with a summary and final revision.
All right, let's kick things off with Section 1, Science in Daily Life, a Legacy of Discovery.
You know, long before modern laboratories were even a thing, early humans were observing natural wonders, things like thunder, gravity, and rainbows. But for a long time, they just explained them through myths. Eventually, though, we realized we needed a better way. We moved away from simply guessing and started carrying out systematic experiments, and that shift gave birth to true scientia. That's the Latin root word for science. Scientia is defined as a discipline involving systematic observations and experiments to understand natural phenomena. It is the framework that lets us collect hard data and make accurate conclusions about how the universe actually works.
And this systematic approach, it directly translates to the rapid technological innovations that impact our daily lives. Because of scientific innovation applied to fields like engineering, communication, agriculture, and medicine, we have completely transformed human society. Just think about communications. We've evolved from lugging around those massive, heavy bricks they called early cellular phones to wearing incredibly powerful, sleek digital technology right on our wrists. Science is literally the engine of our daily progress.
Because science touches absolutely everything, mastering these foundational skills opens the door to so many vital careers across all kinds of distinct scientific fields. For instance, if you're fascinated by biology, the study of living things, you might become a medical doctor or maybe a microbiologist seeking cures for diseases. If physics, the study of matter and energy, grabs your attention, you could be building towering skyscrapers as an engineer or decoding the universe as an astronomer. A love for chemistry leads to crucial roles like being a pharmacist, while earth sciences pave the way for geologists and oceanographers. The systematic investigation we are learning today is your starting point for literally any of these paths.
Moving right along to Section 2, Inside Your Science Laboratory. Let's talk tools and safety rules.
So, as a scientist, you really need to know that every single tool in your lab is highly specific. You can't just grab a random glass jar to conduct an experiment. A beaker, for example, is used for measuring fixed volumes of liquid and mixing them. A boiling tube, on the other hand, is specifically manufactured from much thicker glass. Why? To withstand the intense direct heat you need when warming small amounts of chemicals. You've also got tools like burettes for highly accurate liquid measurement, and conical flasks designed for swirling liquids without spilling a drop. A true scientist knows their apparatus perfectly.
But knowing your tools is only half the battle. Safety has to be your absolute top priority. You are going to be handling materials that demand deep respect. Take lithium, for example. It's a highly flammable and incredibly reactive element. If it gets exposed to normal air or moisture, it will react violently. That's why it literally has to be kept safely submerged in paraffin oil. You also have to learn to instantly recognize critical hazard symbols, like the skull and crossbones warning you of poisonous materials, the flame symbol for flammables, or the large X indicating irritants. Following these safety rules is non-negotiable to prevent serious accidents.
Let's jump into Section 3, Physical Quantities and Units. This is the universal language of science. Okay, so a physical quantity is basically any property that can be measured, and you must memorize these 5 base quantities and their specific units. Seriously, think of this as the alphabet of science. For length, we use the meter. For mass, it's the kilogram. For time, the second. Now for temperature, I know we usually use Celsius in daily life, but the standard scientific unit is actually the Kelvin. And finally, for electric current, we use the ampere. Now, when we need to handle extremely large or incredibly small measurements, we simply add prefixes. We use kilo for 1,000 times the base unit, like a kilometer, or milli for 1,000th of the base unit. It makes scaling units a breeze. These are formally known as the Système International des Unités, or SI units. They have been the global standard since 1960, and there's a really good reason for that. Before 1960, scientists in different countries were just using their own non-standardized units, which led to massive inconsistencies and painful errors in global research. By standardizing, A scientist in Malaysia and a scientist in Brazil can look at each other's data and perfectly understand it. It makes worldwide collaboration possible without any mathematical confusion.
Next up is Section 4, Mastering Your Measuring Instruments. It's all about capturing perfect data.
To capture that perfect data, you have to understand that your measuring instruments must balance three crucial concepts. First is accuracy, which means getting a value closest to the actual true value. Think of it like hitting the bullseye on a dartboard. Second is consistency. This is the ability of your instrument to give you the exact same reading if you measure something multiple times, like throwing 3 darts into the exact same spot. And third is sensitivity. This is an instrument's ability to detect even the tiniest changes in measurement, sort of like a highly sensitive microphone picking up a faint whisper.
Now, even with the best tools, errors still happen, and they generally fall into two camps. Systematic errors are instrument-based. A really common one is a zero error, where a scale or a caliper doesn't quite start exactly at 0. You fix this by calibrating your instrument before you use it. Random errors, on the other hand, are observer-based. A classic example here is a parallax error. If your eyes aren't exactly perpendicular to the reading scale on your measuring cylinder, you're going to record the wrong number. But you can fix this simply by adjusting your posture to align correctly with the tool.
Of course, sometimes a standard ruler just isn't sensitive enough. When you need to measure the thickness of a single piece of paper or, say, a strand of hair, you have to upgrade to high-precision tools. Vernier calipers are amazing for this, offering a sensitivity of 0.01 centimeters, while a micrometer screw goes even further down to 0.001 centimeters. Digital electronic balances give us highly precise mass readings, and this applies to our other base units too. We rely on highly sensitive stopwatches for time, precise lab thermometers for temperature, and accurate ammeters for capturing electric current.
Let's dive into Section 5, Density and the Scientific Process. We are looking at the properties of matter here. One of the absolute most important concepts we can derive from our base measurements is density. By accurately measuring both the mass of an object and the volume of space it takes up, you can calculate its density. The strict mathematical definition is mass per unit volume, and this is critical for understanding whether something is going to float or sink. The density of pure water is 1 gram per cubic centimeter. The rule is simple. If a material's density is greater than 1, it sinks. If it is less than 1, it floats.
And it's amazing how this simple formula explains grand natural phenomena. Have you ever wondered why people can just effortlessly float in the waters of the Dead Sea? It's because the Dead Sea has an extremely high salt content. All that dissolved salt significantly increases the mass of the water per unit volume, making the overall density of the water so high that a human body just naturally floats right on top. And this applies to gases too. A helium balloon floats away into the sky simply because helium is significantly less dense than the surrounding air.
So how does this all connect? It ties together into the ultimate code of our discipline, the scientific method. It works like this. You identify a problem in daily life. You head into your laboratory to form a systematic hypothesis. Doing this correctly relies on mastering the 12 science process skills, things like observing, classifying, measuring, and experimenting. You collect accurate data, actively working to avoid those systematic and random errors. You analyze it all, and finally, you write a conclusive report. That final report is crucial because it's how you share your new discoveries with the global scientific community. Finally, we arrive at Section 6, Summary and Final Revision. Being a true investigator isn't just about using tools correctly. It requires adopting actual scientific attitudes and values. You must practice relentless curiosity about the natural world, ensure complete honesty and objectivity when recording your data, and hold a profound sense of responsibility for the safety of yourself, your lab, and the environment.
So we've covered how science shapes our world, how to stay safe in the lab, global SI units, how to avoid errors with high-precision tools, and how all of this perfectly combines into the scientific method. To wrap up this explainer, I want to leave you with a question. With your new understanding of systematic observation, what natural mystery around you will you investigate first? Keep questioning, keep measuring, and I'll see you in the next one.